Till now in the torsional vibration we have studied simple by Newton's second law how to obtain the equation of motion. Also we have dealt with the transfer matrix method for multi-degree of freedom system. In these cases all the rotors which we considered generally the shaft of such rotors had only the stiffness property, thus we neglected the mass of the shaft. But in practical rotors we find that not only the stiffness, also the mass of the mass or the inertia property of the shaft is distributed throughout the length. So these shafts are very heavy, and because of that they have appreciable amount of polar moment of inertia, and that is distributed throughout the length. So in such rotors generally when we want to model using discrete mass analysis, the analysis is not that much accurate, and for such cases we have approach that is called continuous system approach. Generally we deal with such system with continuous system approach, and today we will see very briefly this particular approach, how to obtain the governing equation for the torsional case when the both mass and elastic property of the shaft is distributed. And our main focus would be in the subsequent lectures to have finite element formulation of such system, so that it can be applied to a real system. So let us see what are the things we will be covering today. So basically we will be developing the torsional vibration analysis using continuous approach, and we will introduce some basic terminology of the finite element method. In this free and forced vibration is the main analysis which we do, and some of the concept like eigenvalue, which is nothing but natural frequency, eigenfunction. In discrete system it was nothing but the mode shape. Some other property like orthogonality property we will see which is there for the eigenfunction, especially for the continuous system. Then some basic definitions which generally we use in the finite element method, like elements, nodes, field variable, degree of freedom of node and element. These are the basic definitions we will be introducing in this particular lecture, and in subsequent lecture we will be dealing with finite element method in more detail. So let us see how this particular continuous system approach works, and for this let us see what are the type of shafts we have considered. So earlier we had one flexible shaft, especially for transverse vibration it is more clear. So I am trying to explain this continuous system approach by transverse vibration, and subsequent then we will be analyzing. So this is a massless flexible shaft and a heavy disc we placed, and such rotors we analyzed by considering only the flexibility of the shaft and the mass of the shaft. In another case we took rigid shaft and flexible bearing. In this particular case the shaft we considered as rigid, only the flexibility was there in the bearing. But in some cases the rotors are relatively heavy and flexible. So when we mount them on bearings, they not only have appreciable amount of inertia, also they have elasticity. For such rotors we cannot able to distinguish where a particular mass we should able to concentrate at one location or several locations. So generally in this particular case we will see that elastic property and the mass property of the shaft we need to consider continuously. This was the example given for the transverse vibration, in which we are interested in this kind of vibration. But the present study, we are interested in the torsional vibration of such rotor system. So let us see how this can be modeled. So for this particular case, if we have a shaft which is let us say this is the axis of the shaft Z, and this is the one of the plane of the shaft shown here, and at a distance Z, let us say there is a plane, the motion of that we want to analyze. In this particular shafts, we have various kind of loading, like we can have distributed torque, external torque acting. So that torque will be representing as function of Z, the axial position of the shaft. Also it is time dependent. And if we have some kind of concentrated torque at some location, which is let us say at location Z0, that is the location of that is fixed. So this will call as a concentrated torque. Now we are interested in a shaft segment which is here. So if we want to see that particular plane of the shaft due to this torsion, so let us say this is y and this is x axis. This is basically center of the shaft, so this will come like this. And if we want to study motion of the point P, let us say the coordinate of that is x, y, z. If we have angular twist of this particular plane phi z, which is again function of z and time, this particular point P will have displacement in the radial direction, which will come at P prime location due to angular displacement. And in this particular hypothesis, we are assuming that whatever the loading is applied on this torque, because of this, if one particular plane which we are considering, that will remain a plane, it will not distort during the motion, and a particular particle on this particular plane like P moves in that particular plane. So you can able to see that in this plane itself it is moving, it is not going out of this plane. Now if we want to analyze the torque balance for a particular shaft segment, let us say we are taking a very small shaft segment having thickness dz, and if we want to draw the free body diagram of that to obtain the equation of motion of this, let us take this particular shaft segment, and this particular shaft segment, as we have seen, the thickness is dz, and once we have taken out from the shaft, the reaction torques will be acting on both sides of this particular plane. So let us say in this particular direction, the torque Tz is acting, which is reactive torque, which is coming from the other end of the shaft, and we have, because inertia property is continuously changing, so we expect that the torque will change at other plane, and this will be given by this expression. even the displacements, angular displacement, I am representing that, let us say positive direction is this one, phi z, which is function of z and t, and this direction also, because from left to right is the positive direction for the z. So here we have the displacement as phi z plus d phi z, change in the angular displacement. Because of this inertia property, there will be change in this particular angular displacement also. So now these two are the torque which are coming on this particular, these are the two torques which are coming onto this particular shaft segment. And now using Newton's law, second law, we can able to obtain the governing equation, and for that we will be equating the torques. So I will take in the next slide. So Tz plus delta t, this is the torque which is acting on the right side of that shaft segment, minus the shaft segment torque and the left plane, and that should be equal to the inertia, rotary inertia of the shaft segment. This now in this, because from torsion theory we know that T by J is equal to G theta by L, so we can able to get the torque as Gj, and this theta is the twist of the shaft segment, which is this, for this particular case is this much, and the length of the shaft segment is dx. So you can able to dz. So you can able to see in the previous slide, the relative twist of the two planes is difference of this angular displacement minus this, so that is the d phi z, and the shaft segment length is dz. So we got this one, and the IP, which is mass polar moment of inertia, is given as r square dm. Dm is the mass of the shaft segment, so we can able to write this as r square rho dv. So this is the mass, and then this we can able to write it as area, and dz, and rho we can take outside, and this can be simplified as rho dz, because dz will come out r square dA, and r square dA is nothing but the j, second moment of inertia, that is polar moment of inertia of the shaft, which is given as j as pi by 32 d4 for circular shaft. So this expression and this expression we can able to substitute in this governing equation. In this governing equation you can able to see that these two terms are getting cancelled, and here we will substitute torque, and here we will substitute IP. So d by dz, or for torque we will write Gj, and this for the torque, and d. So again you can see we have substituted for torque and this one, and right side we need to substitute for IP. So rho j dz and phi double dots. So this is double dot is representing the time derivative with respect to time derivative, and this is a double dot means a double derivative with respect to time. So you can able to see that this will get cancelled, and we will left with equation of motion of the continuous shaft for the torsional vibration, which will be given as like this. So, this is the equation of motion of the continuous system. In this particular case, we did not consider the external torque, but if we want to consider external torque in the previous slide, here we will be having external torques. So, you can able to see that if we want to consider the external torque, here we will be having distributed external torque and concentrated torque, which was at the location of the Z0. So, we will be using a direct delta function delta to specify that particular torque. So, you can able to see this direct delta function is having property that when we have this will be equal to 1 when we have Z is equal to Z0, and this will be 0 when Z is not equal to Z0. So, you can able to see that when we are specifying the Z is equal to Z0, then only this will act, otherwise it will not act, because this is a concentrated load and this is the external load which is distributed over certain length that will be specified. We have obtained the equation of motion of a continuous shaft for its torsional vibration. We have seen that this particular equation of motion is partial differential equation. It is having derivative with respect to Z, the spatial derivative, and as well as derivative with respect to time. And this particular equation of motion represent because till now we have not considered any boundary condition. So, if we consider boundary condition, the solution of this particular differential equation, which we will be calling as boundary value problem, will be unique. So, let us take very simple example of a cantilever shaft. For that, we will solve this particular differential equation, and this particular equation is having similar form, which generally we study in the mathematics. There is we call it as a wave equation. So, this equation is exactly same in form as wave equation, only thing is the variables are different. So, now let us see, we will solve this particular wave differential equation for the boundary condition of the cantilever beam. So, we have one shaft is having cantilever condition. You can able to see this is the Z axis, length of the shaft is L, and it is undergoing torsional vibration. In this particular case, you can able to see that at the fixed end, the boundary condition is that this particular displacement, which is function of time and Z at Z is equal to 0, this displacement is 0 at this fixed end. On the other hand, this free end, there is no torque, and we have represented torque earlier like this. So, at Z is equal to L, we have the condition that torque is 0 because this is a free end. Now, to solve the differential equation which we had obtained earlier, that is I am writing again, phi Z is equal to dj phi Z dz. We will be using the separation of variable method to solve this, and in this method we assume the solution in such that we have two parts of the solution. One function is purely spatial coordinate dependent, that is z, another is time dependent, and this time dependent function is generally harmonic in nature, and the form of this particular function, harmonic function, we know is cos omega n f t plus b sin omega n f t, where omega is a frequency, t is time, a and b are constants, and a and b we will be obtaining based on the initial condition of the problem. From the initial conditions we will be obtaining these two constants. Now, if we take let us, because in this particular equation we can able to see that we need to take time derivative of this particular function and also the special derivative here, and so now I want to differentiate this twice with respect to time. So obviously this will not derivate this chi function, only it will derivate the eta function, which is time dependent. And if I want to differentiate this with respect to z, so that will go into the chi. I am representing that as prime to represent the derivative, partial derivative with respect to z, and this will be as it is. So these two we can able to substitute in the equation of motion, and if we substitute this in equation of motion, we will in the previous equation here, so we will get rho j eta double dot this chi z. So this is in the left side is equal to, in the right side we have, because this particular shaft we have considered a uniform, so Gj will be constant, so it will come out. So we will be having Gj and double derivative of that function, so we will be getting chi double derivative with respect to z and eta t. Now if we see the harmonic function is having property, this particular, if we take double derivative of this with respect to time, basically we will get a relation as this. This is the condition of the harmonic motion, and if we substitute this here, we will get rho j minus omega square n f and chi z eta t is equal to Gj chi. So you can able to see that this chi will be common and it will get cancelled. So we will left with a differential equation which is now only function of z. That means this is now ordinary differential equation. You could able to convert the partial differential equation to ordinary differential equation. So this will be having the form of this. And here this j will also get cancelled, and this we can able to write it as chi t by del square plus, I am calling that constant as alpha square, chi t is equal to 0, where alpha square is, as we can able to see here, is rho omega square n f by capital G. G is the modulus of rigidity. Now this particular differential equation, which is now ordinary differential equation, we can have the solution of this sorry, this is only z, function of z, not function of time. So the function of the solution of this will be of this form: c constant cos alpha t alpha z plus d sin alpha z. So this is the solution which we are assuming of this differential equation, where c and d are constant, and that will be obtaining from the boundary condition of the problem. And for cantilever case which we are dealing with, we have seen that these are the two boundary conditions. So from these two boundary conditions we will be obtaining the c and d value. So let us see the first condition, that at z is equal to 0, this displacement is 0. So we will get this as 1 plus d into 0. So you can able to see that we are getting c is equal to 0 from first boundary condition, this fixed end boundary condition. Second boundary condition we have is this torque is 0. Because eta, here in place of phi z we are writing the assumed solution, this solution, and because there is a differentiation with respect to z, so this will be differentiated, this will be outside this one. So this is 0. So that means we need to derivate this with respect to z first, and we need to substitute here. So we can able to remove this quantity. Also this will not be 0. So I am differentiating this, and we know that c is 0 itself. So only we need to differentiate this d alpha cos this. So this is the derivative of this particular term, and at z is equal to 0, z is equal to L, this quantity is 0. So if we substitute d alpha cos, instead of z we will write L is equal to 0. So you can able to see either d, if it is 0, then the whole motion will be 0, because c is already 0. If d is 0, motion will not take place. We are not interested in that. So d cannot be 0. So for that case, this alpha in general cannot be 0. So we need to have a function, this cos alpha L is equal to 0. So this is the frequency equation. This is the frequency equation, and the root of this will give us the eigenvalues, and from there we can able to obtain the natural frequencies. So you can able to see the solution of this alpha L is equal to pi I by 2, where I can be odd numbers, and we have infinite number of solutions. So infinite number of eigenvalues are possible, and earlier we have related alpha with the natural frequency of the system by this relation. So we can able to get the natural frequency from this, that will be as I pi by 2L. So after simplification we can able to get the natural frequency from these two expression like this, and here I is again varying from 1, 2, 3, 5. So these are the various natural frequency of the cantilever shaft. Now the eigenfunction, the assumed solution we had c is equal to 0. So eigenfunction is left nothing but psi chi is equal to sin alpha z. That again we can able to, and here some constant we can able to attach, and alpha is already given there. So this will be phi I z by 2L. So, this will be the eigenfunction, and eigenfunction will give us how the relative points in the whole shaft will be having displacements, because in this particular case each and every particle point on the shaft will be having relative displacement with respect to each other. This function will give us the relative displacements of various particles in the shaft system. Continuous system approach, as we obtain the natural frequency and the eigenfunction which represent the mode shape. In continuous system, because the mass property is continuously distributed, so basically this system can be considered as an infinite number of degree of freedom, because each and every particle are independently moving with respect to each other, and we have seen that we are getting infinite number of natural frequencies because we have infinite degree of freedom in the continuous system approach. So, now whatever the eigenfunction we obtain, let us see the plot of that for first three modes. So, this is the plot of the eigenfunction. So, you can able to see this is the position of the shaft, this is the fixed end of the shaft, and this is the free end of the shaft, and this is the angular displacement, and this is a relative angular displacement. So, we have taken the maximum displacement as unity, which is for this particular case for first mode. So, this is belonging to the first natural frequency corresponding to I is equal to 1. So, this is the first mode, and for second natural frequency the mode shape will look like this. This is the fixed end, maximum is taking place here and here also, here plus minus and here minus 1. This we are normalized because this is a relative displacement. So, the maximum we are taking as 1, but here you can able to see that if we draw the 0 line, there is a one place where the shaft displacements are 0. So, and either end of this particular shaft is having opposite angular displacements. So, this particular position is called node, as we have seen earlier also. So, there will not be any angular displacement of the shaft at this particular place, but either side of this two will be having opposite motion. Again I am repeating, we are talking about the torsional angular displacement. So, the shaft shaft particles which are left side and right side, they will be having opposite motion. Similarly, this is the third one is for third natural frequency, and here if we draw the 0 line, we will see that there will be two nodes where there will not be any angular displacements, but there will be angular displacement in either side, and this two will be having opposite motion and this two will be having opposite motion. So, and we can able to plot this for higher natural frequencies also, and we expect for such cases additional nodes will be coming as we will increase the natural frequencies. For the continuous system approach, we have obtained the natural frequency and mode shape for one particular boundary condition. This was cantilever case. In continuous system approach, we can able to obtain this natural frequencies for simple boundary conditions, and few more boundary conditions solutions I am providing here. So, like we have if free shaft is there is no support at both ends, then the natural frequency will be given by this expression. Here the eigenfunction will be having this function, sine function, and for another case in which both the end of the shaft is fixed, In this particular case, natural frequency will be given by this, and the mode shape will be like this. Is also sine function, but there is some difference. This is the fixed free case, this is fixed case, and this is free. So this is fixed free, this is similar to the cantilever, this is a cantilever case, this is fixed and this is free, and these are the natural frequency and mode shape. So basically we need to satisfy the boundary conditions to get the constant, that C and D, and depending upon that we can able to get the this equations. Once we obtain the eigenfunction for a particular disturbance, if you are talking about free vibration, if you are giving a disturbance to the system, how the system will vibrate will be given by the expansion theorem, in which we mention that any free vibration we can able to express in terms of these eigenfunction, contribution from these basic eigenfunctions, and contribution of various eigenfunction will depend upon the initial condition. So let us see this particular torsional free vibration, how we can able to express in terms of the eigenfunction. So this is for the case for the simply support for the case of the cantilever beam case. So this was the eigenfunction, and this is the harmonic function. So you can able to see that we are expressing any general free vibration in summation of various eigenfunction and the harmonic function, where A and B is the contribution of various modes, and this will depend upon how we are giving the initial conditions. And for zero initial condition like this, if our initial conditions is not zero initial condition, at time t is equal to 0, for initial condition t is equal to 0, if we have these angular displacement and angular velocity, these constants we can able to get by this. Basically, to get this we need to multiply both sides of this equation by the eigenfunction for one particular mode, and we need to integrate over the domain. And while integrating, we will be using the orthogonality of the mode shape. That means when these two mode shapes are same, when they are not same, then this is 0 and this should be equal to. So when they are same, then it will not be 0. So when two eigenfunctions are same, this quantity will not be 0, and when these two eigenfunctions are different, then this will be 0. So you can able to see that once we are applying multiplying by in both sides by eigenfunction of the ith mode, the terms here will be 0 corresponding to all modes except I, and that is the case here. So these have been obtained using the this orthogonality condition of the mode shapes. So you can able to see for different initial conditions we can able to get these constants, and the free vibration can be described. We have analyzed the torsional vibration. The analysis for the axial vibration for continuous system is exactly similar to the torsional vibration. Only thing is some of the variables we need to interchange. So for axial vibration, so if we are talking about a shaft having axial vibration, that means longitudinal vibration. So if you want to analyze this system, we need to replace the angular displacement which we took in the torsional vibration by axial vibration, that is a linear vibration, and the J second moment of area, the polar moment of area, we need to replace with A, G we need to replace with E, and torque we need to replace by force. So these will be the changes in the equation of motion and otherwise the analysis is exactly same. Differential equation, eigenfunction, everything is same, only we need to replace these variables, then we can able to analyze the axial vibration. So, we will not be repeating the axial vibration analysis here, but just we are trying to show the analogy here. In the continuous system approach, as I mentioned, for more complex boundary condition or for multiple disk or multiple support, the obtaining solutions are not easy. I will just show one particular case in which the same cantilever beam in which we have this shaft is having continuously distributed stiffness and mass property, but along with that there is a concentrated disk at the free end, and this addition of the disk, how the complexity increases because of this, we will try to see. So, we have in this particular case a cantilever shaft having distributed mass and stiffness property, and there is a concentrated disk at the end. Let us say the polar moment of inertia of that is IP. So, in this particular case we can able to see the boundary conditions. This particular disk either we can take in the boundary condition. So, fixed end the boundary condition is same, that is this is at z is equal to 0 is 0. Here to obtain boundary condition, let us take the free body diagram of the disk. So, in this particular case, if this is the positive direction for the angular displacement, there will be reactive torque from the shaft onto this, that will be acting, and that will be this at z is equal to L. So, from this we can able to get the boundary condition here. That means, if we take the equation of motion of this, because this particular torque is acting in the negative direction, this is the only torque acting on this particular disk, should be equal to this is at z is equal to L, should be equal to inertia. This is the polar moment of inertia of the disk, and phi z z at z is equal to L. Because this disk location is at z is equal to L, this angular displacement, which is basically in general representing the displacement, angular displacement of the whole shaft at any location of the z. So, we need to specify that this angular displacement which we are talking about for this disk is at z is equal to L. So, this is the equation which we obtain, is the boundary condition of the problem. Earlier, because there was no disk, so right hand side was 0, but because there is a disk, this is having right hand side which is this. Now, let us see how this boundary condition gives the complexity in the solution. So, we had the equation like this, in which C and D we need to obtain with the boundary condition. So, for this boundary condition, because this phi z we chose as multiplication of this and the time function. So, in this particular case, time function is not there. So, basically we can able to write this as, so I am satisfying here. So, xi at 0, eta t at this is at z is equal to 0 is 0. So, you can see eta t c plus d into 0. So, this we already seen that for this particular case, because eta cannot be 0, c, this gives the c is equal to 0. This was the similar condition as the previous one. The complexity is there in the second boundary condition now. So now we need to substitute here the solution. So I am taking this in the second slide. The boundary condition I am rewriting. Like this, and because we have the harmonic function eta, so we can able to write so basically here if we substitute this here, we will get negative of that, we will get negative of this. So they will get cancelled. Now we will satisfy the boundary condition. So you can able to see that if we take the first derivative of this, because c is already 0, so this will be this similar to the previous one. We have substituted for z is equal to L is equal to so here also we have substituted for this. So we can able to see that now this equation we can able to simplify as tan alpha L is equal to rho g L by IP 1 by alpha L. So with some rearrangement we can able to write this equation like this. So here you can able to see that the solution of this is not easy, because we need to solve for alpha, which is here also. So this is a transcendental equation. So this we need to solve numerically, and few solutions of these I am providing here. But we will be having infinite number of solutions. So first 3 solutions are these. And once we obtain this, because we know alpha and omega NF are related, so natural frequency can be obtained. But you can able to appreciate that with the addition of the mass itself, the frequency equation which was earlier simpler, now it has become a transcendental equation, and solution of those roots are not easy now. So in the present lecture, we introduce the continuous system approach for torsional vibration. This particular system is most accurately we can able to model the system, we can able to get the natural frequency and eigenfunction, but the difficulty is for very simple boundary condition we can able to get the solutions. For more complex conditions we need to go for approximate solutions, and in the subsequent class we will choose finite element method for solution of such system, in which will be, because we know that finite element method is having flexibility in incorporating more complex boundary conditions. So that particular method will be exploring in 2 lectures. In this continuous system approach, as we have seen that we solve the system equations as a whole. In the subsequent lecture we will see, when we will be using the finite element method, in that particular method we break the system in various small segments that we call it as element, and we obtain the elemental equation. And once we obtain the elemental equation, then we obtain the system equation by assembling such elemental equations, and then finally we apply the boundary condition to get the governing equation for the whole system. So that particular method we will see in the subsequent lecture. Today we will be doing the torsional vibration using the finite element method. So basically I will be introducing the finite element method which will be useful for purpose of the analyzing the torsional vibration. We will not go into more detail on the finite element method as such, but how it can be used for analyzing the rotors for torsional vibration we will try to highlight. And then we will, through some examples, we will try to see how this particular method is having capability to analyze more complex rotor system as compared to either analytical method or Newton's method. The transfer matrix method we already seen, it can handle large systems of rotors, and so let us see what are the things we will be covering in this particular lecture. So, we will be analyzing the torsional vibration by finite element method. Free and forced vibration, both we can able to do it with this method. Various concepts of the finite element methods like elements, nodes, field variable, degree of freedom of a node or of an element, interpolation or shape function, and two conditions which we need to satisfy of the interpolation function, that is a compatibility condition and the completeness condition. Based on these we will be choosing the interpolation function. So, we will introduce these terminologies, and then once we have discretized the system into various elements, how to obtain the elemental equation, and from those elemental equation how to get the system equation and application of the boundary condition in the system equation, so that either we can able to solve for free vibration or forced vibration of the torsional vibration. So, now with a very simple case we will try to see how the finite element method works. In the continuous system approach, we have seen that the governing equation defines for each and every particle onto the system. So, that particular equation represents the governing equation for the whole system. But in finite element method, we will see that we will first discretize the system, we will break the system into various pieces, and then we develop the elemental equation for each of them, and then system equation can be built. So, let us take one case in which we have a cantilever shaft like this. One end of the shaft is fixed, another is free. For finite element method, we need to break this particular shaft into number of pieces depending upon the accuracy required. These size of each of the shaft segment can vary. Here I have taken uniform. So, if total length of the shaft is L, each element, because we are divided into 5 element length, if it is uniformly divided, in that particular case we will be having length is equal to L by 5, and each of this shaft segment will call these as element. So, element 1, element 2, element 3, element 4, element 5, and between the two elements there is a common interface, and those we call it as a node. So, we have node 1 here, node 2, node 3, node 4, node 5 and node 6. So, these are the node positions, and in finite element method we will try to find out the solution at these node positions, and we will see that we will be if we want the solution in between, we will be using some kind of interpolation function to obtain that. And if we want to develop the elemental equation, so we can take one of the representative element and we can draw the free body diagram of that. So, if we draw the free body diagram of one of the element, so let us say this is the one of the element, I will enlarge it. Let us say this is the eth element, and to define the location of this element, I am attaching a coordinate system which we call as local coordinate system. In the actual system, we can have a coordinate system which is, I should call this as capital Z. So, this is defining a axis system which is global axis system. This is local to this element. Now, the length of this element is L, small l. Our node here is, let us say, ith node, and this is jth node, and at each of this we now want to specify the field variables. So, obviously, field variable is at ith node, we have angular displacement phi z I, and here angular displacement phi z j, and their directions we are taking in left to right as positive. So, both are having the same direction at two nodes at j and I and j. Apart from this, we will be having the torque associated with this displacement. So, I am writing here torque as T. This is the reaction torque from the other element. So, T r I, and here T r j. The direction of this torque is also same as the displacements. We are taking same as the displacement, and depending upon their actual direction, the positive or negative will take care of the actual direction. So, this is an element of the shaft system for torsional vibration, and you can able to see that at each node one field variable, that is the angular displacement, is there. So, this particular node is defined by this field variable, a single field variable for this particular problem. This is another node, there also there is another field variable. So, for one element which we have considered here, there are two nodes and the elemental degree of freedom is 2. So, one is phi z 1, phi z 1, and phi another is phi z j. Now, we because whatever the governing equation we derive for continuous system, which was valid for each and every particle in the whole system. So, obviously, that governing equation will be valid for this element also, but in this particular case, as I mentioned, we will be seeking the solution at the nodes only, and if we want the solution in between, solution means the angular displacements in between, then we will be using some kind of shape function. So, that means in this particular case, this particular shape function in finite element method is generally a polynomial. So, this is the angular displacement of an element. So, superscript E is representing this is the angular displacement for one element, which is function of both axial position and time. We will be representing this as a polynomial. So, polynomial will be having some constants like a, b z plus c z square. We can take this as several terms depending upon the problem. We need to truncate this polynomial up to certain degree of the polynomial. So, you can able to see that in this interpolation function some unknowns are appearing, and these unknowns we will be finding from the boundary condition of the element, because this solution which we are assuming is for this element. So, we need to find out these constants from the boundary condition of the element. Now, once we have chosen the solution in this form, so we can able to see that in this particular case boundary conditions is z is equal to 0. Here we have angular displacement of the element at z is equal to 0 is phi z I, and at z is equal to L, other end of the element, we have this angular displacement at L is phi z j. So, we expect that these constants will be in terms of these field variables at node I and j. So, that means this particular solution which we is in a more general form can be written like this: phi z element z t is equal to, here we can able to write in terms of some functions which is function of z. There could be several functions. Number of functions will govern by the type of problem we are dealing with, but in general we can able to write like this, and here we can have various field variables. So, this is a more general representation of the assumed solution, in which we have taken r number of field variable. For the present problem, r is 2. So, we expect only 2 terms here and 2 functions here, and this in more compact form we can able to write this as n this is for the nodes. So, you can able to see these field variables are defined at nodes, node 1, 2 are at node. For present case r is 2, so up to second will be coming. So, n e is representing that these field variables are at the nodal position. These are the function of z, which will be of the form of polynomial, and actual form of this will be obtaining depending upon the boundary condition of the present problem. So, this is the solution for the element, and we can able to appreciate here, because we are using polynomial and we need to truncate the polynomial at some degree. So, this solution is approximate in nature. So, once this solution is approximate in nature, if we try to satisfy this solution into the equation of motion, so obviously that equation of motion will not satisfy completely. There will be some residual, and now we will be trying to see how this assumed solution, approximate assumed solution, can be substituted in the governing equation, and how we can able to derive the elemental equation for the element which we have chosen. So, we will be using a Galerichan method for this. In this particular method, whatever the residual comes after substitution of this assumed solution in the governing equation, we minimize that particular residual. So, let us say r is the residual for that particular element. So, we multiply this by some function. So, in Galerichan method we multiply by these functions, which are we call as shape functions, and we integrate this quantity over domain or whole length of the element, and we equate it to 0. So, that whatever the residual is there, that is distributed over the length, and because we can have these shape functions are in number depending upon the degree of freedom of the element. So, that many equations will be getting from this method. So, now let us see what is the form of the residual. The shape function will at present keep in the general form, and subsequently we will be obtaining the explicit form of this particular shape function. So, let us see the residual, because we earlier derived the governing equation which was having this form for continuous system. So, this is double dot derivative with respect to time. This is function of both z and t. Then I am representing the double derivative with respect to z as comma double z. So, that means phi z, this is same as like this. So, this representation is more compact. So, I am using this representation, and this phi is function of z and t. And if we have external torque which is function of which is distributed torque, so this one, or if we have concentrated torque at particular location in this particular element. So, this will be function of time only, and we will be using the direct delta function z minus z naught location. So, here if the torque is within the element, then only it will contribute, otherwise it will not contribute. So, if z naught is within the element, then only it will be appearing. Similarly, the external torque which is distributed, if it is there within the element, then it will be having contribution in the equation of motion. So, this equation of motion which we written earlier, only difference here is you can see instead of only phi z, I am writing the superscript e. So, that means we have written this for element, because this governing equation is valid for each and every point on the system. So, it is valid for this element also. So, you can able to see this is the this is representing for the element, and because these solutions are approximate, so this will not be perfectly 0, and this quantity we will call it as residual, which is function of z and t. So, the whole quantity is residual. Now, we want to minimize this particular residual as we using the Galerkin method by multiplying by the shape function and equating it to 0. So, this is the Galerkin method. So, now I am substituting the residual which is here in this in the next slide, and so I will get terms like this. So, within bracket the residual I am expressing. So, this is the residual term. Basically, this is the inertia term, and this is elastic torque term, comma z z means double derivative with respect to z, then external torque which is distributed, and concentrated torque which is located at one location at z is equal to z naught. So, this was the residual. We are integrating this and over the domain and equating it to 0, where this I is from 1 to r depending upon the degree of the freedom of the element. Now in this particular equation, because we are using the assumed solution in the form of polynomial, you can able to see that here we have second derivative involved with respect to z. So whatever the polynomial which we need to choose, that should have at least quadratic term. So that means, because if you are taking up to only the linear term a and b, the second derivative of this term will give this quantity 0. So here this term will be 0. So this is not a complete representation of the polynomial of the assumed solution. So for this particular case, you can able to see at least we need to go up to the quadratic polynomial. We can take more also, but at least quadratic is required. But by some mathematical manipulation, we can able to reduce this particular differential order. That we will see how we can able to reduce the differentiation order, so that we can able to use lesser degree polynomial that will be having a lesser requirement in the computation. So let us see how we can able to. So what we will be doing? We will be doing basically integration by part of this term with respect to z. So first term is as it is, there is no change in the first term. Only terms containing the double derivative with respect to z, we are doing integration by part once. So here I am writing this in more explicit form, 0 to L g j dz, and other terms n I is there, T external distributed, and T naught, which is concentrated torque. Okay. So now I want to do the integration by part of this term. I am doing this separately here. So this term will be as it is, minus in this let us say n I is the first part and remaining is the second part. So we can write this as g j n I. This is the first part, integration of the second part, that means phi z, one derivative will reduce here and limit is 0 to L, then because is negative here, 0 to L, we can have differentiation of the first part and the second part integration dz, and the torque term, this external torque term will remain as it is, equal to 0. So main term which we have manipulated is the second term. So you can able to see this is the first part, integration of the second part, limit, and then differentiation of the first part and integration of the first part. So now you can able to see in the whole expression the phi z is having derivative of single only. So we could able to now use lesser degree polynomial without compromising on the terms. So you can able to see even if you are taking a linear polynomial, the terms will not vanish, and this particular requirement is called the completeness requirement. Of shape function. So, we have seen that how we evolved the requirement of the shape function. One of the requirement, that is a completeness requirement, that so we should choose the polynomial such that when we substitute in the formulation which shown, it should not vanish. So, in the formulation, we after the integration by part, we could able to reduce the order, and that is why this particular step is called weak formulation in the finite element method, in which from polynomial requirement to the linear requirement of the shape function, we could able to reduce. So, this requirement we could able to weaken it. So, that is why this particular step is called weak formulation, and you can able to see now that now we can able to have the explicit form of the shape function. To get the explicit form of the shape function, obviously now we have seen that the linear polynomial is good enough for this particular problem from the weak formulation. So, now we will obtain the explicit form of the this shape function using the boundary condition of the element. So, for this case we chose one element and we had ith and jth node, and there the field variables were these two, phi z I and phi z j, and local coordinate system was z. So, we have boundary condition that at z is equal to 0, phi z I is phi z is this for element, phi z e, all are element because we are representing for this particular element only. Similarly, at z is equal to L, we have another boundary condition, that is phi z j. Now, once we have the form of this elemental field variable in the form of polynomial, as we have seen in from the weak formulation, okay, this is good enough, and you can able to see that there are two constants and we have two boundary condition. So, in that way also we can able to obtain the explicit form of A and B in terms of this nodal displacements. So, first condition if we satisfy here, so we will get this as phi z I for element. So, A plus B into 0. So, from here we can see A is phi z I, and from the second boundary condition we have this A plus B L, and that is equal to phi z j, this one. And now we already know A is this one, so B can be written as phi z j minus phi z I for element divided by L. So, you can able to see that we could able to obtain the A and B, and this we can able to substitute in this equation, phi z I plus phi z j, this is for all for element, phi z I divided by L, and z is here. So, the assumed solution now contain the field variables and the z, which is polynomial. So, this equation we can able to rearrange, we can able to collect the terms of the phi z I which are here, and phi j is single term. So, we can able to write this as this assumed solution in the form of polynomial can be written as 1 minus z by L phi zi plus z by L phi zj. Now, with some manipulation we can able to express this as 1 minus z by L this is representing a row vector. This particular symbol is representing a row vector and this is representing a column vector. So, you can able to see if we multiply these two vector, we will get the same expression as the previous one. This is the column vector, this is the row vector. Now, if you recall, we wrote this as earlier n1 z and 2 z, and here we have the same thing. And these n1 and n2 are the shape functions, and these are the nodal displacements, and we wrote this in the more compact form as shape function row vector and the field variable at nodal location. And now we will see the property of this two shape function. If we see n1 is 1 minus z by L and n2 is z by L. If we see the element having this axis, total length is L. So, if you want to plot the n1, so let us say if you want to plot n1 here, so at z is equal to 0, which is this location, the value of n1 is 1. So, this is 1, and at z is equal to L, this quantity becomes 0. So, is here, and is linearly varying in between. So, this will vary like this. N2 at z is equal to 0, it is 0 here at z is equal to 0, and at z is equal to L is having one value. So, is one value, and in between is varying linearly. So, you can able to see that how this interpolation function changes, and from this we can able to obtain the so this is Ni, and this is corresponding to node I, and this is corresponding to node J. So, you can able to see that if we want the value of this field variable at z equal to 0, this will be 1, this will be 0, and that will be giving us the field variable at ith node. If it is z is L, and I will be 0, this will be 1. So, we will be getting the field variable at the jth node. But if we put z in between, then it will interpolate the field variable from this field from these nodal displacements, and we can able to get the field variable at any other, or the angular displacement at any other location. So, basically here all these corresponding to the I and jth node are there in the previous case also. So, now we have seen the property of the shape function. We have obtained the explicit form of the shape function for this particular element, in which only we had two nodes and we had 2 degree of freedom of the element. Now, we will see another property of the shape function which we need to satisfy, that is the compatibility condition. The compatibility condition is between two nodes or two elements. We have seen the completeness condition we satisfied within a particular element, but this compatibility condition we need to satisfy two elements at the common node. So, if we have two neighboring elements and there is a common node in between, then let us see what is this compatibility condition we need to satisfy. So, basically we have divided the shaft into various elements and we have drawn the free body diagram of that, and during assembly obviously we need to join all those elements, and during joining there has to be some compatibility, that the displacement predicted by one element at one particular common node and displacement predicted by another element at the same node should match. That is the compatibility condition. So, let us see through how we should whether this particular shape function which we have chosen is compatible up to the requirement for us. So, in this particular case, basically if we go back to our equation, weak formulation equation. So, in this within the integral, whatever the highest derivative of the field variable is there, we need to satisfy the compatibility condition one order less. So, this is the, I should say, thumb rule, that within the integral in this weak formulation we have first derivative of the field variable. So, we need to satisfy the compatibility condition one order less. In transverse vibration we will see that these derivatives will be having higher order, and we need to satisfy even higher order field variable derivatives, but for this torsional case only we need to satisfy the compatibility of the field variable itself. There is no need to satisfy for the its derivative with respect to z. So, with this rule of the compatibility condition, let us see how we can able to check this condition for the chosen shape function. So, we have two neighboring elements, element E and element E plus 1. The common node is J, this one is I node J and K. J is the common node between these two elements. So, now for element E we can able to write the field variable using the shape function. Here you can able to see they are corresponding to node I and J field variable. Similarly, for element E plus 1, the expression this is the field variable for E plus 1, shape function remain the same, and here the field variable at the nodes will be J and K. So, using these two we can able to predict. So, from first we can able to predict the displacement, angular displacement in the E element, and from second we can able to predict for the Eth element. But at common node we can able to predict from this element also and from this element also, and we need to see that this prediction should be same or not. So, let us see for Eth element, if we substitute J is equal to L, which is corresponding to the jth node. So, if you see back for this element, for J is equal to L, this is the node, this is the local coordinate system. So, if we put Z is equal to L, this N1 will be 0, and I will be 0, and J will be 1, and if we multiply this, we are getting the field variable at the jth node. Now, if you take element J plus E plus 1, then the jth node location, this is the E plus 1 element, local coordinate is again is starting from the same point here, but node is J here and K here. So, you can able to see that for element E plus 1, the jth node is at Z is equal to 0. So, that is why we are trying to predict the field variable at jth node by putting Z is equal to 0 in the E plus 1th element equation. So, in this particular case, N J will be 1 and this will be 0, and you can able to see after multiplication we are getting the field variable at the jth node. So, both elemental both are giving, both elements are giving the angular displacement at common node as same. So, we call these as they are compatible. So, this is the compatibility condition satisfaction. So, whatever the polynomial we have chosen in the form of shape function, they are compatible for the present problem. Now, once we have chosen the explicit form of the shape function, you can able to see the previous equation which we had for I is equal to 1 to r. We had r such equations because ni was there in each of the expressions, and those equation we can able to put in a single equation in the vector form. So, here now r is 2 for present case. So, this is the same weak formulation equation which we are putting ni in the form of a vector. So, you can able to see the form of n will be for present case n1 and 2. So, basically if you expand again, you will get two equations out of this. Similarly, here because there was derivative with respect to z. So, I am writing this as basically this expression is n1 comma z and 2 comma z. Comma z is representing that we need to derivate the shape function with respect to z once, both the shape functions. And here this is the other term which is after integration by part we got an additional term, and these the external torque terms, distributed torque and the concentrated torque. So, this is the term which we got after integration by part. So, this limit shows that particular term. Here also we have put the all those ni in a vector form, so that we can able to represent this in a more compact form. Now, having obtained the shape function, and in this particular equations we need the derivative of this with respect to z of shape function. So, the shape function we can able to derivate once, and because only the shape function will get differentiated, this is time dependent. So, this will not get differentiated with respect to z. So, this is the field variable which is function of both z and t. This is the field variable at node which is function of only time only. So, this is the difference. So, this is for the whole element, this is for the element, that is why it is function of time only, and in between we interpolate using this interpolation function, and this comma z is representing derivative with respect to z. So, because we know the form of this, so we can able to differentiate this to get 1 by L and 1 by L, because we know once we differentiate we will get this quantity, because z was there, 1 is constant, that will vanish. Similarly, if we differentiate with respect to time, this term will get derivated and will be. So, these two terms we can able to substitute in the above expressions. So, this I am substituting. So, we can able to see I am getting a column vector of n and row vector of n from this, and because this is time dependent, so it can come out from the integral. Similarly, from second expression, this is row vector, column vector, row vector, which is coming from here, and this time dependent term I am keeping outside. And here I am writing in a more expanded form like this, and this is a torque, external torque. So, I am keeping this as it is. Now, you can able to see the same equation I have written in more explicit form. This is exactly same equation as previous one. Only thing here I am substituting for the limit. So, in previous case we had this one, and I am substituting the limit. So, in this you can able to see for z is equal to L, this will be 0 and 1 will be 0 and 2 will be 1. So, this will give me this, and similarly for z is equal to L and 1 will be 1 and 2 will be 0. So, we will get this. So, basically these are the reaction torques at the two ends of the shaft, which I am representing as this particular vector. And this term I am calling as a mass matrix. This term I am calling as a stiffness matrix, and remaining this term I am expressing as the external torque term. So, this is the reactions because we have divided into element, and this is the element, this is the external torque. The explicit form of this mass matrix will be like this. So, if we multiply this, this will be the explicit form of the mass matrix. Similarly, the stiffness matrix we can able to multiply. So, this will be the explicit form of the stiffness matrix. This we already expanded the reaction torque terms. So, this will be reaction torque term at one of the ith node, and this for the jth node, and this is the external torque. So, in the present lecture we have seen how to formulate the elemental equation for torsional vibration. We started with the very basic concept of the finite element method. First we need to discretize the system into various parts that we call it as element, and we took one of the element and we obtained the governing equation that we call it as a finite element equation for that. And this particular finite element equation, the form is similar as we have standard equations in the vibration, which contains the mass matrix, stiffness matrix, reaction torques and external torque. Damping we have not considered in this particular case. And once we obtain this elemental equation, in the next lecture we will see how these elemental equation can be used to analyze more complex system, or how we can able to solve a system equation, because this equation is representing for one of the element. So, similar equation we need to write for all the element in the system, and then we can combine them, and then boundary condition can be applied to get the system equation, and that can be solved for either free vibration or forced vibration. So, you can able to appreciate once we take up with some example how this particular method is can tackle various kind of boundary conditions, and even for large system the formulation is easy. So, is more once we have these elemental equations ready, we can able to make a computer program for analyzing more complex system, and that will see the subsequent class overall procedure how we can able to solve a bigger system.